The point of this video is to give you the main ideas behind one of the key results from this course, which is that in theory, there's a way for you to establish a link, or a semi-conjugacy, between a general map F on the real line to the shift map. Now you'll remember that we had done something very similar for the logistic map, where we defined the motion of the map as akin to shifting of binary sequences, where each symbol of the sequence indicates if the map sends a point to the left or to the right. The key is that if you look at the points that are sent, say on the left, these points will be stretched out to cover both the left and right. So F sends I0 in this graph to both I0 and I1. We say that I0 F covers I0 and I1, and this turns out to be a crucial property for chaos. Here's the theorem. The theorem says, firstly, let I from 0 to n-1 be a collection of disjoint, closed, bounded intervals on the real line, and let I be the union of all these intervals. Let F be a map on the real line, and let lambda be the invariant set. Let A be the transition matrix of F covering relations for I. Then the theorem states that F restricted to lambda is then semi-conjugate to sigma defined on the transition matrix A. There are essentially three pieces we need before we can prove the theorem. The first is to show what an F covering is, the second is to define what a semi-conjugacy is, and the third is an important lemma. I've written II and IJ here, but let's just call it I and J. First, we say that the interval I, F covers the interval J if F of I literally covers J, or if you like, J is a subset of F of I. So in this diagram, you see the original I interval on the top, from which F then sends to another interval that covers J, shown on the bottom. So in theory, you can analyze a graph to find all the covering relations for whatever intervals you're interested in. For example, in this graph, we're interested in the interval I0 shown in blue and I1 shown in red. Notice that for this particular graph, F sends I0 to this region delimited by the braces, which then covers I1. On the other hand, F sends I1 to cover both I0 and I1, shown in the red braces. So the covering relationships are summarized either with a graph, with arrows indicating F covers, here I0 F covers I1, I1 F covers itself, and I0. Or we can summarize this with a transition matrix A. The next thing we need is semi-conjugacy. That's easy. The definition appears in chapter 9, but I'll summarize it even more simply for you. First, you need to remember what it means for F to be conjugate to G. You need to find a map H such that H of F of x is equal to G of H of x, H is injective or 1-to-1, H is surjective or onto, and H inverse are continuous. For semi-conjugacy, you simply remove the need for H to be injective and for H inverse to be continuous. That's what it means to have a semi-conjugacy between F and G. So now let's turn to the lemma. Let I and J be closed intervals. If I, F covers J, then there exists a closed subinterval, K, in I, such that F of K is exactly equal to J. Here's a picture of why, in some cases, this lemma should be obvious. On the top picture, you see I, F covers J, as shown by the red dashed lines. Because of the continuity of the map, you then expect that there's a smaller piece of I, called K, that perfectly equals J. But here, now is a picture of why it's not so obvious. There's no guarantee that F sends I in a clear way to J. So if we look at the pre-images of the endpoints of J, they don't necessarily map to only a single point in I. The trick is for you to simply take the rightmost point of the left intervals, called U here, and the leftmost point of the right interval, called it V. You know that any point between U and V then maps exactly to J by the continuity of the F map. Let's prove this. Let J be given by the interval between P and G, and this is now closed. Look at the pre-images F inverse of P and F inverse of Q. These must be closed and non-empty by the covering assumption. Set U to be the supremum of F inverse of P, or the largest element x, in I such that f of x is equal to P, and then similarly set V to be the infimum of F inverse of Q. This is the smallest x in I such that f of x is equal to Q. So U was the largest of the left possible endpoints, and V was the smallest of the right possible endpoints. You then let K be the interval between U and V. So now we pick any S in J, which is within P and Q, and we have to find a point that maps to this S. Okay? Now we already know that U is mapped to P and V is mapped to Q, but let's also assume that P is less than or equal to Q. If Q is greater than or equal to P, then the graph below has a negative gradient, but the proof is very similar. So, we want to find a point between U and V which maps to the point S, which lies between P and Q. But the graph is continuous, and this follows by the intermediate value theorem. So formally, we can write this. Let g of x be equal to f of x minus s. Then you know that g of u, which is equal to p minus s, has to be less than or equal to 0. And g of v, which is equal to q minus s, has to be greater than or equal to 0. In other words, the g of u graph is less than or equal to 0 on the left, is greater than or equal to 0 on the right, so it has to go through 0. Therefore, there exists a w in u and v such that g of w is exactly equal to 0, and hence f of w is equal to s. Therefore, every s in J has a pre-image in K. QED. Let's now come back to the theorem. The proof of this theorem proceeds very similarly to the proof of the analogous theorem for the logistic map being conjugate to the shift map. You need to prove or find three things. First, define an H that sends points in lambda to points in the sequence space sigma Na. Show that H is surjective, or onto, and show H is continuous. I'll give you an idea of the first and second points, and you can refer to the notes for the more complete proof. First, we need a map from the invariant set X to the sequence space. Remember that you've divided the original interval I into a union of disjoint closed intervals I0, I1, I2, and so forth. We define it very simply. Given X on the real line, you track which interval each iteration of the map sends the point. So for instance, on the graph on the right, you see that X is sent to I0, then I4, then I113. So the sequence would be 0, 4, 113, and so forth. You can verify that this H has the property that H of f of x is equal to sigma of H of x. We now need to show that H is surjective. It will be sufficient for us to understand how it works with a graph. Our goal is to show that given a sequence A equal to A0, A1, A2, and so forth, we can always find a point x in lambda that maps to this sequence. In other words, if you hit x with fj times, then the interval in which it lies has to match the interval that's listed on the jth symbol. Here's the basic idea. You know that x has to start in IA0, shown in the blue brackets. You also know that on the next iteration, f of x lies in IA1. By the lemma, you know there's a smaller interval in IA0 that maps exactly to IA1, and this is shown in red. Great. So you've narrowed down the possibilities where x may be. Let's narrow it down further. On the second iteration, you know the point where it has to lie is in IA2. but you know there's a subinterval of IA1, here called IA1A2, that maps exactly to IA2. This is shown in red on the second line. But then you know there's an even smaller interval, shown in black, called IA0A1A2, that lies within the red brackets. Thus, you've narrowed down the possibilities even further. At this point, with a depth of 3, you've found that x must be in IA0A1A2, and this guarantees that the point must match the sequence to a depth of 3 symbols. You can continue by induction, and what forms is a nested sequence of closed, non-empty subsets. Hence, by the Cantor intersection theorem, their intersection is non-empty, QED.